guys like you don't need them. Okay. Yeah. So background, X86 instruction set actually is a logical successor from the very earliest microprocessors, which is why they do some pretty weird things. But the earliest ones, the 8008 chip and then the 8080 chip, then its successor, the X8086, that's where we get the X86 from. All interesting chips, to put it mildly. And I've worked with all of them from the 8008 on up, which came out in 1972. Okay. So let's talk about what this chip is. I'm going to cover basic X86 register model. If you don't understand the register model of a computer, you're kind of lost. Instruction set somewhat. Addressing modes, these are important because there's all kinds of addressing modes: immediate, direct to memory, register to register, and I'll explain what all of that means for those of you who aren't that familiar. And then we'll show you how to disassemble code, what's really going on in your C++ program. Okay. So a little bit of background knowledge. Obviously, some of you don't have this, so I'm going to go through some of it. Your basic computer architecture, though, John von Neumann, I think 1946, I may have that date a little off, but not very much, decided that, gee, one of the things we could do with a computer, instead of having to rewire it every time we wanted to change the program, is store the program as data in memory in the computer and have something that interprets these instructions and executes them as data, in effect. So the instructions are stored as data, and there's a program counter, a register built in, that determines which instruction is next in memory to be addressed, and I'll show you all of this. And then there's a decoder that figures out what instruction it is, add, load, whatever, multiply. And then the ALU, the arithmetic and logical unit, actually runs it, does whatever the instruction says it's supposed to do. But before that, anytime you wanted to reprogram a computer, you had to change the wiring. So this was a huge innovation, made things a lot easier, a lot more flexible, and that architecture is still with us, right? All these machines are using that basic John von Neumann architecture design. Obviously, things have changed a lot. There's another sidebar on von Neumann. Once he had invented this and they were able to write more complex programs, his programs had problems. And he realized that he was going to spend a lot of his time finding errors in his own work. How many of you can identify? Every one of us, right? Unless you write perfect code the first time. Very few of us do. I've had maybe 3 programs in my life, or 4, that worked the first shot. That's it. Okay. And I'm assuming that you have some understanding of binary and hex, because I will be showing it to you, and ability to program in C or C++, or both. Okay. About the X86. These are not RISC machines. Okay. These are a long way from the RISC architecture. That architecture has a real design plan, as opposed to, well, we only have so many transistors, so we can only have these instructions, which was the X86 or original chips. What the RISC architecture did, IBM did a study, and they looked at millions of lines of code, and they realized that, gee, of all the instructions this machine can execute, they're only using this subset. And these instructions they use very rarely. Well, let's get rid of them and just make the ones that we have really fast, and anything that we don't have as an instruction we can do by multiple instructions. Okay. Like the earliest processors didn't have a multiply instruction. Well, you can write a multiply subroutine. Okay. So that's what they did. But that was the plan behind RISC. These are not RISC chips. Okay. These are amazing. There is stuff in here you wouldn't believe. So the X86 contains 2 separate instruction sets, in effect. The original X86 or 8086 instruction set, which was a 32-bit set, 16-bit, But the X8086, even though it was a 16-bit instruction set, had a 20-bit addressability, and I'll show you how that worked, using base registers and offsets. We also won't cover the X64 architecture. That is another animal entirely again, which 64-bit addressability, meaning, so what's 2 to the 64th? That's 4 billion times 4 billion, roughly. So large number, okay. 32-bit addressability is 4 gigabytes, which these days, that's not much, is it? Okay. How much memory do you have in that machine? 8, yeah, okay. And that's kind of a minimum that you can buy today, right? My phone has 8, no, 16. Phone has 16. So, you know, that's kind of a minimum these days. So now you need the additional addressability beyond 32 bits, right? So the X64 architecture. We're not going to go there yet. Floating point operations are done, interestingly, by a separate processor core. On the earliest IBM PCs, which this is all the logical grandchildren of, it was a separate chip. So if you wanted floating point, there was a socket next to the 8086 chip or 8088 chip. You plugged in the separate chip. And then instead of emulating floating point in software, you would actually have floating point in hardware. That was a really interesting architecture, the way they did that one. It's a stack machine. So what you do to use floating point is you push 2 operands on the stack, and then you execute, let's say, a floating point multiply, or a x to the y, all done in hardware, and then it would pop the 2 operands, do the operation, push the result onto the stack. So it was beautifully designed for a parsed arithmetic expression. Perfect, right? We're not going to cover that, but I want you to know about it. Okay, so there's all this stuff hidden in these boxes we all have. And so we'll open the covers a little bit. So I've talked about CISC versus RISC. One of the things, though, is that these instructions, even though they're complex, because of the design of the chip, they can do quite a lot in a few clock cycles. Some of them are only 1 clock cycle. Let me explain clock cycles. You know that you've heard the terms, right? This is a 3.2 gigahertz or a 4 gigahertz processor. That means that the clock is running 4 billion times a second, changing state. So, for example, a register-to-register adding 2 numbers that are in a register, typically takes place in 1 clock cycle, meaning that you can do 4 billion of those a second on a machine like this. Okay. Who saw Hidden Figures? Anyone? You should have. She's talking about how incredible it is that the machine can do something like 30,000 operations a second. Okay. That was not bad for that time period, right? Late 50s. Today, of course, you know, it's a doorstop. Well, actually, it's not a doorstop because it wouldn't fit through the door. We remember from Hidden Figures, right? Anyway, so clock cycles give you an idea of what that is. So every time the clock pulses, one more step, sometimes one step of an instruction, sometimes a whole instruction takes place. Okay, so the register model, then, registers are special locations in memory. They're actually in the CPU. They're not cache. They are separate, just highly specialized memory locations is the way to view them. Inside the CPU, we have the original 8-bit set from the 8088 or 8080, A, B, C, D, E, and then H and L were addressing registers. You could only address stuff through using these 2 registers to point to a memory location. And the original chip, 8008, had only 8 bits on the address bus. So what happened if you want to address 14 bits worth of memory, what's that, 16K of memory, K, not meg, not gig, was to put the first 8 bits out on the bus. They would be latched, and then you put the other 8 bits, or in this case 6 bits in the earliest chips. So that's why we have the LSB, MSB, or little endian architecture in all of these successor chips, because of the way that original chip worked. So in the X86, we have 16 8086 registers, AX, BX, and so forth, and their 8-bit counterparts, AH and AL, okay, high and low from the AX register. AX, A extended to 16 bits, okay. Then we had the source SI and DI registers. These are 16-bit registers as well. Source index, destination index. There are some interesting instructions that will move data around very quickly. If you ever decompile or disassemble, for example, memcopy, C function, you will find that that's what it does. And it does it very cleverly, in fact. More on that later. Segment registers. This is how we got 20-bit addressability with 16-bit registers. What they did is the segment registers are 20 bits wide, but the low 4 bits are always 0. Okay, is the way to look at it. I'm going to draw here for a moment. I hope some of these work. So if you have, yeah, right. Let's use this one, I think. Can you see this okay? Oh, the cheap seats. Okay. So you have a 20-bit 19 through 0. And if you add that, the high bits to a 16-bit register, okay, and these are 0, okay, and you extend it, then you have an offset, which is 20 bits, or actually 16, but you add it to the high end of this. So you can, wait, did I do this right? No, this goes here. Or 15 through 0, okay. So, but these bits added to the address, they're always 0. So these high order bits then get you 4 more bits of addressability. So you can address now, instead of 64K of memory, adding 4 more bits. So 64K, 128, 256, 512, and 1 meg. So you have 1 megabyte of addressability. According to Bill Gates, that should be enough for anyone. Right. Bill Gates talking in 1983. I think he's changed his tune now. But this is how they did it. It's kind of a kludge. You know that word, right? Maybe you've even done one. But it worked, right? It got us a lot more addressability. And then there's stack registers, stack pointer and base pointer. These allow the processor to do functions extremely well. So if you use the stack right, what you can do is address off the stack pointer into a stack frame, and now you have your local variables, which is very hard to do, by the way, with a lot of RISC machines. You have to write a lot of code to do this. But with the X86, it's all built in, wired into the hardware. In fact, in the later stuff, there's like starting, I think, with the 386, might be the 286, there's an enter instruction that is the function call entry that builds a lot of this stuff for you as one instruction. Now, it's a multi-cycle instruction, but it does a lot for you. We're not going to, go into too much of that. So this is the 16-bit and the 8-bit. Okay, now 32-bit registers, 386 and later. So now we have EAX, that's extended A extended, okay? Or, as you might say, overextended A register, way overextended. EAX, EBX, and so forth. Extended SI and DI, those are 32-bit registers now in their own right. You still have the segment registers, and they've added 2 more, FS and GS, which I haven't needed in any of the code I've written, but they're there, okay? So this is, again, just building up to how things work and where things are. Status flags. Overflow the result exceeds the positive or negative limit of a number range. So a 32-bit number is minus 2, basically 2.1 billion to positive 2.1 billion. You can make it overflow, and unless you use these status flags, you won't know, right? Unless you check the sign and see how the sign changed from one operation to the next. So sign bit, the result is negative if it's set. 0, the result is 0. Carry, this is interesting. Carry out of the most significant bit of the result. So if you add two numbers and you get a carry, then you know that something, it's like overflow, but it's not exactly overflow. And what we did with the carry, this is interesting for the early processors, you won't need it in the current ones, but there's an instruction called add with carry, ADC. And what it would do is it would add two numbers and the carry bit. So the carry bit would be added into the lowest order bit, but otherwise it was an ordinary addition. So what you could do is if you wanted to add large numbers, instead of having to do your own computation, you could simply add the first two, then ADC the next one, and if there was carry out, then you got that carry carried over into the next bytes of the numbers you're adding, and so forth. So it's very useful to see that. Auxiliary carry, this is amusing, why it's in there is historical. Carry out of the bit 3 position. Okay, why is that useful? Well, it says used for BCD. Nobody knows what BCD is anymore. Binary coded decimal, you know, okay. They explain in architecture, or did you just know?
I don't remember what I learned from.
Okay. Yeah, because I'll be teaching architecture next semester for the first time since 1976. So hasn't changed that much, right? It was a complex instruction set on that machine. So it's going to be kind of fun. Binary coded decimal, the way they did this, probably should start incorporating some of this into the talk, right, into the slides. But what they did, no, this board. Yeah. Is in 1 byte, you store 2 decimal digits. Binary, but 2 decimal digits. So this byte can hold 0 through 9. This byte can hold 0 through 9, but is binary. So like, let's say we have 5, 0, 1, 0, 1, and 7, 0, 1, 1, 1, okay? What can happen is if we add, let's say we add something to this, we add 7 to the 5 here, 0, 1, 1, 1. If we get a carry out of the high bit, then we know that we need to add that carry into the next BCD digit. So this was a really convenient way of storing numbers where you don't have to do binary arithmetic. You can essentially do decimal arithmetic as binary as long as you play by the rules. So it worked really well. Again, it's not used a lot. I used it in a lot of early programs, not so much anymore. A lot of the early IBM hardware used this too. And of course, I programmed a lot of that early IBM hardware because that was what there was. So machine instructions then have a format, and in X86 there's a prefix, which is optional. There's an opcode, which is not optional, an operation that to be performed, not optional. Register specifier, also optional. Addressing mode specifier, optional. Scale index and base byte, which contains information, again, optional. A displacement, an offset essentially from a base, and potentially immediate operands. So everything except the opcode is optional. One of the instructions, mildly amusing, is no op. It simply says, don't do anything. Why would you want that? Well, I've used it, yeah. Why are you raising your hand?
So it's a long story, but I have a very good reason why X86 is
Okay. Well, no, long story. Where I've used them is if I'm going to do self-modifying code, I have a no-op or 2 or 3 or 10, and then I can put the the self-modifying code over that, which, can we spell ugly, boys and girls? That is, it's a venial sin at the least, right, to do self-modifying code. The other place I've used it is in timing loops, which also, so you want no ops and you just spin in a timing loop and you have a certain number of no ops. So two reasons why you might want, yes, sir.
You wouldn't usually be the one coding them though. At a CPU level, when you're in a pipeline CPU, sometimes you just need to wait for a couple cycles to make it work.
Right.
You might not be coding it, but the processor needs to be able to do it.
Yeah, so that's another way. Yeah, I haven't seen that too much. I've used it mostly in timing or self-modifying code, which, you know, these days self-modifying code is harder to write because the code segments are read-only or execute only. So there's a lot of stuff in the newest processors that make it not possible to do that stuff. But it's still fun to play with, right? You can turn off that bit if you're at the right level, privilege level. So again, the only thing required is the opcode. Operand selection, okay? All operations affect the state of the processor. Even no op, it affects the state of the program counter, which is a special register that determines what instruction will be executed next. So that's a register I didn't point out, but it's there. You modify it by sequential execution. The branch instructions modify the program counter. You branch to someplace, okay, program counter has changed. So that's effectively loading the program counter. Most of them have some operand, explicit or implicit, that gets changed. So operand locations I've listed for immediate, contained in the instruction. So for example, I can write something like this. Move EAX, comma 1. And what it does, this is an immediate operand. The 1 is immediate. It says, put this value, 32-bit value, into the extended AX register. Okay. MIPS, again, has stuff like this. So immediate operands, they're in the instruction itself. In a register, so they can be in any of these registers. Memory, okay, so you can address memory, and there's lots of addressing modes that gets interesting. Or at an I/O port. And X86 has actual I/O ports, instructions for doing I/O. I've worked with processors that don't, which are interesting. What they typically do is they do what's called memory mapped I/O. I'm getting a little further afield, where if you address a particular memory location, that does I/O. And the way those work is there's a chip, usually a programmable gate array, that looks at all the addresses and says, oh, this is addressing this memory location. We really want to do I/O on this I/O port. If you look at the Raspberry Pi, it's all memory mapped addressing for the pins. And I think everything else too is all memory mapped addressing. So, you know, again, fun stuff. So, questions so far? Reasonably clear? Okay, good. So implicit and explicit operands. Most things have explicit operands, but things like AAM, ASCII adjust for multiply, okay, which essentially is a BCD adjust for the multiply, always operate on AX, period, or EAX. So what it does is that after you do the ASCII multiply, it fixes the result and makes it actual BCD. Most require you to specify operands like exchange, XCHG. What that does is it's one instruction, swaps the contents of two registers. Okay, does this look useful? Yeah. You know, we all coded bubble sort using 3 lines of code. There you go, right? So this won't actually do it. I'd have to look. Can you have 2 memory operands for exchange? I'd have to look. I think you can only have a memory register operand, not two memory operands. So you'd have to load one of them into memory and then exchange it with memory. So you could do it in two instructions. What would be interesting is to look at what C++ Visual Studio generates for that swap function, right? Things like push AX have both. What this does is it explicitly puts AX on top of the stack and implicitly changes the stack pointer and the contents of memory. So there's, as I said, a built-in stack. You can push registers onto the stack. You can push memory onto the stack, which is kind of interesting. So if you're saving state, a lot of the time, one of the ways of saving state is to push registers onto the stack, at least in the old days. The other thing is, of course, the arithmetic instructions change the contents of the flags. So if you, for example, add two numbers and you get an overflow, it changes the contents of one of the status flags. If you subtract two numbers and you get 0 as a result, it sets the 0 flag. Right? All of this stuff is in there. So again, most instructions, one of the two explicitly specified operands may be in a register or memory. The other operand must be in a register or it must be immediate. So here's some explicit two operand instruction groups: register to register, which I mentioned, like the exchange that I just showed you, exchanges, forget now, BX with EAX with EBX, okay? So register to register. You can also do register to register addition, multiplication, so forth. A lot of these things work register to register. The advantage is that it's fast. Register to register operations are, sometimes they're one cycle, sometimes they're two or three, but they're a lot faster than accessing memory. Okay. Register to memory. So you do an arithmetic result and you want to store the result in an arithmetic operation, you want to store the result in memory. Okay. You can move AX, comma, some memory location or any register. Memory to register. So, for example, you have something in, let's say you're summing an array. So you load a register with 0, and then you iterate through the array, and you just add to that register from each memory location using an index. And I'll show you how some of that works. Immediate to register, like I just showed you, move EAX, comma 1. Immediate to memory. You can also move an immediate operand to a memory location. So immediate, again, the operand is in the instruction. So I can say move memory address, comma 1, and it will put that 1 in some memory location. Okay. And one of the things that is interesting, I'm glad we're teaching C++ as the intro language. Java is just too high level of abstraction for me for this. You don't really get a sense of what's happening in the hardware. But in C++, we can look at what's happening in the hardware, and we will. Immediate operands, though, here's some more. So some instructions use data from within the instruction as one or sometimes two of the operands. So it can be a byte, a word, a double word. Byte is, again, 8 bits, word is 16, double word considered to be 32 bits. So for example, shift right, EAX, comma 2, shifts the register right 2 bits. What is this the equivalent of, by the way?
Dividing by 4, right?
Yeah, dividing by 4. And I think this one doesn't extend the sign. Okay, so there's all kinds of shift operations which are equivalent to multiply and divide by powers of 2, right? So this one, shift right, is equivalent to dividing by 2. Okay, integer multiply multiplies the contents of memword by 3, immediate operand, memory operand, and puts the result in CX. Okay, so again, lots of stuff here, but this one uses both a memory register and an immediate operand. Cool, yes? Yes, sir.
What's the I mean?
Integer. Yeah. Yes, sir.
What's the maximum amount of arguments a single x86 instruction can have?
The most I've ever seen is 3. So this is kind of the outer limits of instruction operands. I won't guarantee that. Yeah.
Are most of these base arithmetic functions, are there explicit ones for register, memory, or do most of them accept multiple?
Yeah, what they did is the mnemonic, instruction mnemonic will be the same. So like move or imul. But what the assembler does is it looks at the operands and then generates the addressing.
Oh, like an overload function. Okay.
Yeah, overloaded instructions, if you like. But I think they're the same opcode. They're the same mnemonic, same opcode. Something in there tells it what the operands are. I say that. Could be the prefix, although the prefix, the way I've seen it used, is like the rep prefix to repeat something, things like that. Like there's a move instruction, and if you execute it with a rep prefix, SI and DI get incremented and CX gets decremented. Right? So it's essentially memcopy as one instruction. Right? All of this stuff is in there. Okay. Memory models. This is interesting too. This has changed a lot. Flat memory model maps different logical segments to one physical address space. I mean, if you think about it, there's one physical address space anyway. You have that 8 gig SIM. It's 0 through 8 gigabytes, 8 billion roughly, right? So it's flat address space. What a lot of this determines is not so much what's there, but how you see it, how you address it, how you look at it. So all segment registers map to the same place, and since you have a 32-bit, or in the X64, you have a 64-bit, you can address the entire memory without having to worry about segments. The value of segments, of course, was what I showed you with the 20-bit segment register. And I liked using these even so, because then I could keep, for example, code segments, data segments, extra segments all separate. So segment register holds 16-bit pointers, these original ones did, there's extended ones, to a table in memory that holds the base address of the segment and other information. So instead of the segments in the current processors being just an offset, now it's a pointer to a table in memory somewhere that gives you the offset and things like execute only. So a lot of that's in the newer stuff. Okay. So you can optionally specify a segment for memory operands and a lot of instructions. Here's the rules if you don't specify a segment. Instructions always use the code segment. So if you're executing instructions, you can set the CS register, which typically when a program loads, the CS register is set by the operating system. So that gives you the code segment, and then the offset is always 0, which is really convenient. When you load a program, you load it into location 0, offset by something, and then you don't have to worry about relocating it at load time, which a lot of older computers had to do. Or you don't have to say, oh, this only runs in this part of memory, which also was done. I mean, there's a lot of tricks to this. Stack uses SS, stack segment. Local data uses the data segment. Destination for some string instructions, like string compare, string move, string search, I'll show you these, uses the extra segment and in combination with the DI register. You can use segment override prefixes. So I did a lot of this in one of the big programs that I wrote, where specifically in an interpreter for one of the languages that I wrote, compilers, the actual interpreted instructions, the byte codes, if you will, are stored in something that's addressed off the extra segment. So now I've got my data segment for local data, and then my actual program that I'm interpreting is run off the extra segment. So I use segment overrides for all of that. You can't override instruction fetch to stat or destination strings. Okay, those you're stuck. So one of the things then we have, and I know this is starting to get awfully detailed, isn't it, is effective address computation. Because the address that you actually have in the instruction may not be the actual memory address. There's an effective address that gets computed, and the way it's computed is this mode RM byte provides a lot of flexibility. So they have this byte after the opcode. They're really common, a lot of them. And what they say is memory operands specified in this mode, the offset within the selected segment is the sum of 3 components. So the offset, the actual memory address, is a displacement, the base register, one of those segment registers, and an index, which may be multiplied by a factor of 2, 4, or 8, or 1 implicitly. So you can work on bytes. So here's the addressing modes, and I'll show you some of this in real code here in a few minutes. I realize that if you've taken a programming class from me, we've gotten through how many minutes without actual code? You must be getting nervous by now. Okay, so you have a displacement only, like move something to memory specifically, just a displacement. You have a base, move something to a base address only. Base plus displacement, okay, so that's indexed essentially. Well, not indexed, base, yeah, just a base address plus some offset from that base address. Index times some scale factor, 0, 1, 2, or 1, 2, 4, or 8, plus a displacement. A base plus an index plus a displacement, okay, or a base plus an index times a scale factor plus a displacement. All of these addressing modes work. They work really well. And of course, you have data element sizes like 8 bits, 16 bits, 32 bits, and then in the latest chips, X64, 64-bit. Okay. The other thing that you should know about, almost last slide before we hit code, you can look at source code and disassembly of a lot of the C++ runtime. So I'm going to copy this, which means I have to exit yeah. And we're going to look for this. Control C.